here it will be convenient to use X to denote just an IID sequence like we usually do. So I will rename Brownian motion and denote it by WT. So we'll denote it as WT for T non-negative. Okay, and then we'll consider some IID sequence xi for I greater or equal than 1, such that these random variables will be centered and we'll have a finite second moment or finite variance. So we'll denote by sigma squared the expectation of x squared, which is we assume to be finite. And our usual random walk is given by just the sum of these x1, xn. Okay, and what we'll do here is rescale both time and space for this random walk. Okay, which we'll do as follows. So we'll denote by WTN to be the following rescaling. So in the space we'll rescale by 1 over square root of n times this sigma, or standard deviation, and then in time we are going to sum not up to n but up to n times t. So given this time parameter t, we are going to sum xi up to t times n, okay, where this is just the floor function. So we just round down n times t to the closest integer. Now we want to stay in the space of continuous functions because we want to prove convergence in the space of continuous functions. So here we'll just artificially add a term which interpolates when our time parameter is in between two terms. So here, if you think about this for a second, you can simply add nt minus this floor function and then include the next term. So nt plus 1 divided by square root of n sigma. This makes this process continuous in t. So the purpose of this term is to be a continuous interpolation, okay, when the time parameter is in between k over n and k plus 1 over n. Okay, and so we define this process for all non-negative times. And our goal will be to show that this continuous process converges in distribution to a Brownian motion. And the motivation for this is pretty clear. It's just the central limit theorem. In particular, for simplicity here, I'm not going to write the last term, which is just added there for continuous interpolation. So it just adds some notational difficulties in terms of writing. So for simplicity, when to see the main idea of the proof and kind of ignore technicalities, let's simply think that the nt is integer, and so we just write this first term and sum up to nt. Okay, and if you do that, then you can see that by central limit theorem, so here you are adding n times t terms. So you would like to divide by square root of the number of terms, so square root of nt. And then the central limit theorem tells you that this converges in distribution to a standard Gaussian times square root of t. So this converges in distribution to Gaussian with variance t. Okay, and that already shows us that for a fixed t, this rescaled random walk converges in distribution to a Brownian motion, which was defined to have Gaussian distribution with variance t for a fixed t. The same holds for finite dimensional distributions, right? Because if you look at the increments of this rescaled random walk, right, you can see that Wtn has, well, again, essentially independent increments. And moreover, this process is also essentially stationary, right? Because when you look at the increment of the process between, let's say, time s and time t, if you ignore the interpolation term, which is small since you scale it by square root of n, you're just summing between ns and nt, right? And it's the same thing as summing starting from 1 n times t minus s terms, right? And moreover, on different intervals, because our sequence xi iid, these sums are independent of each other. So by central limit theorem, you also have convergence of finite dimensional distributions, right? So if you take this process or rescaled random walk at finite number of times up to tk for some t1 tk, you have convergence in distribution as n goes to infinity to a Brownian motion at times t1 tk. Okay, so for any t1 tk. So in other words, the finite dimensional distributions converge. And in order to conclude that these processes converge, as processes on the space of continuous functions, it just remains to prove the uniform tightness of this sequence, right? So the result that we want to prove, and this is the Donsker invariance theorem, so that as a process, this converges in distribution to a process which is a Brownian motion on the space of continuous functions on positive half line. Okay, this is exactly the statement of the Donsker invariance theorem, and it will hold if we can show uniform tightness. So, okay, if we can show that the sequence of these processes is uniformly tight on this space of continuous functions, or more precisely, their distributions on this space is a uniformly tight sequence of distributions. Okay, and so to prove this Donsker's theorem, in the rest of this video we are going to check the above condition that guarantees uniform tightness of this sequence. Now all these processes are 0 at 0, so when t is 0, all of these are 0, so we do not need to check the first condition, uniform boundedness at 0. So we only need to consider the second condition concerning the modulus of continuity. Okay, so we take any positive t and then write the modulus of continuity of this process Wn a little bit more explicitly. So by definition, this is just supremum over any two t and s in 0t within a distance delta from each other, the increment of that process, which will result, again, just for convenience, if we ignore the linear interpolation term, this will be just a sum between ns and nt of our random walk xi. Now let's write this supremum as a maximum over all possible integer starting points and ending point for this sum. So really what this means that we have to take any integer between 0 and n times capital T. And then the increment should be at most size delta. So in other words, we take any integer up to n times delta, right? And then we consider the sum between k and k plus j of xi. Okay, so we have finitely many starting points, k up to n times t, and then we have finitely many choices for the increment. Now, first thing that we need here that will be important in this proof is to notice that we can discretize the starting point kn. Okay, so when we look at this maximum here, we are going to consider the integers which are actually proportional to this increment n delta. So let's consider integers of the form 0. Now, n delta is not integer, but again, just for simplicity of notation, I'm not going to round down and simply write n delta, 2n delta, 3n delta, and so on. And we go up to nt, so this is also n delta times t over delta. Okay, so here we have t over delta terms. We split this interval into intervals of length n delta. Now, when we look at this sum here between k and k plus j, so j here is on the scale n delta. Okay, so let's kind of zoom in and consider the sum between k and k plus j, right? So we have a sum like this. And so let's consider a particular interval proportional to n delta where this k falls. So here you have some L times n delta, and then here maybe you have L plus 1 times n delta here. Okay, and then what we'll notice is that you can represent this sum between k and k plus j as a combination of this sum here, then this sum here, and then this sum here. Okay, so let's call our original sum by s, and let's call this first sum here s1, this second sum here s2, and this third sum s3. So the s then can be written as s2 minus s1 plus s3. Okay, notice in this representation, the starting point in these three sums is either L n delta or L plus 1 n delta. So the starting point is proportional to n delta. But at the same time, arbitrary sum that we are interested in can be represented as a linear combination of three sums with this discretized starting point. So in particular, if we let's denote by m this ratio t over delta, so in other words, the number of starting points in this discretization, right, in this interval here, then because any sum can be written as the three sums of this form, we can just by triangle inequality write that the maximum as above. So for any starting point k and any increment j of the sizes that we want of our rescaled random walk or increments of the random walk, okay, we can bound this from above by three sums as above. So in other words, we can start at points of the form L times n delta. So now we can consider m minus 1 of these L's, and J will be the same as before. Okay. And in this sum, instead of K, we start from L times N delta. Okay, because all the sums above S1, S2, S3 are of this form. In other words, the K was discretized to some finite number independent of N, right? And we only lost the factor of 3 here. So when we take a limit when N goes to infinity, this will really help us in the calculation that will follow. Okay, so in particular, when we look at the event when the modulus of continuity exceeds some epsilon, right? So we want to control the probability of event of this form. So if this happens, then now this maximum on the left hand side here is exactly the modulus of continuity. So it exceeds epsilon. It means the right hand side exceeds epsilon over 3. So in other words, if the right hand side, the maximum on the right hand side exceeds epsilon over 3, there exists this L up to m minus 1 such that the maximum over J exceeds epsilon over 3. Okay, and so given this observation, we can control the probability that the modulus of continuity of this process Wn at delta exceeds epsilon. It means one of these events should happen. So for one of the L's, this maximum should exceed epsilon over 3. And so by the union bound, first you can just write it as a sum, or bound this by the sum over L, the probability of this event here, right, that this maximum exceeds epsilon over 3. Now notice that each of these events has the same probability because you're just summing IID random variables. So for L equal to 0, it's the same as for every other L. So this sum is just m minus 1 times the same probability for L equal to 0. And here we recognize that we have already dealt with this type of object when we want to control the maximum. And in particular, we can use the first Kolmogorov's inequality. So we are going to control this probability here. Let's recall Kolmogorov's first inequality. Okay, the Kolmogorov's inequality states that if you look at the sums of this form for independent random variables, if you have a control of the probability for the tail, so if for all j up to n, you can control probability that Sn minus Sj exceeds some level alpha by some probability strictly less than 1. Okay, then you can control the probability for the maximum of the partial sums. So the maximum over all j up to n, the partial sum Sj exceeds 2 alpha. This can be bounded by 1 over 1 minus p, the probability just for the last sum n exceeding alpha. So in this case above here, we are summing up to n delta. So the role of n will be played by n delta. Okay, and then to check this first condition, we are just going to use Chebyshev's inequality. So by Chebyshev, if you want to control the probability that the tail, so Sn delta minus Sj, is just the sum between j and n delta of our sequence xi, that it exceeds some alpha. Now, in this particular case, we're going to take alpha to be epsilon over 6 square root of n sigma. Well, basically because then 2 alpha will match exactly after rescaling in this inequality. If you multiply both sides by square root n sigma, then you will get square root n sigma epsilon over 3 on the right hand side, and we want this to be 2 alpha. Okay, then this probability that this exceeds epsilon over 6 square root of n sigma, you just square both sides and you get by Chebyshev's inequality, this is bounded by 36 over epsilon squared n sigma squared times the sum of variances, because these guys are IID, so that just gives you sigma squared variance of one term times n delta. Okay, and so you get the upper bound for this probability, 36 delta divided by epsilon squared. And in particular, for a fixed epsilon, we are trying to find a small delta. If you look at the statement, so delta will go to 0 in the end, and so you can make this as small as you like when delta goes to 0. So you can make this less than 1. Right, and then applying the above inequality, we get control of the probability for the maximum of partial sums. So here we get the probability that the maximum up to n delta of the partial sums up to j exceeding 2 alpha, so that's epsilon over 3 square root of n sigma, so that's exactly the probability above that we want to control. By this Kolmogorov's inequality, this will be bounded by 1 over 1 minus p, so 36 delta divided by epsilon squared times the probability that the final sum up to n delta exceeds alpha, so epsilon over 6 square root of n sigma. And this is the place where we will use this relaxation of the second condition, that we can actually take the upper limit as n goes to infinity first, before sending delta to 0. So as a result, here when we take, so let's take the limit or lim sup when n goes to infinity of the probability that this modulus of continuity for the process Wn at delta exceeds epsilon, right? So we bounded this probability, and as a result this will be bounded by lim sup of, above we had the factor m, which was actually t over delta, and then we have this factor 1 over 1 minus p, and the only thing that really depends on n is this final probability, that the sum up to n delta exceeds epsilon over 6 square root of n times sigma. Okay, but by central limit theorem we know what the limit of this probability is. So again, recall here that m was just t over delta, then 1 minus 36 delta epsilon over 2, and this final probability, to apply a central limit theorem here, right, we just recall that when you sum up to n delta xi, if you scale by square root of n delta and by the standard deviation, right, this will go in distribution to the standard Gaussian, to some random variable g, which is standard Gaussian. And so in the above probability, by central limit theorem, this you have to rescale, by this 1 over square root on delta sigma, and then this results in the limit in the probability that standard Gaussian exceeds epsilon over 6 square root of delta, right, after such rescaling. Now we are basically done, because we can now apply the control for the tail of the Gaussian probability that we have already seen before. So let's leave the first two factors as they are. And so this final probability, because it's two-sided, you can control it by twice e to the minus 1/2 times this constant square. So epsilon squared over 36 delta. And what we want is for this to go to 0 when delta goes to 0. Right? And we can see here that indeed this is the case, because the main dependence on delta is through this exponential here. So this will clearly dominate. This will go to 0 faster than this factor 1 over delta grows in front of the exponential. Okay, so this whole thing goes to 0, and we proved that the limit when delta goes to 0, the lim sup when n goes to infinity, for this probability that the modulus of continuity of the process Wn, which is this rescaled random walk, exceeds epsilon, is 0 for any t and any epsilon. So this proves that the sequence of the distributions, of the laws of these processes on the space of continuous functions is uniformly tight. And as a result, this finishes the proof of the Donsker's theorem that as a process, this rescaled random walk converges to the Brownian motion on this space of continuous functions that we considered in the beginning. Okay, and let's finish just with a quick summary here of this last proof, because there were several technical points that went into this proof. And so just as a summary, first of all, let's recall that the first main step was characterization of uniform tightness using this modulus of continuity by way of their Arcelor-Ascoli theorem. So uniform tightness specifically on the space of continuous functions where processes live. And then in this particular case of random walks, this modulus of continuity was expressed as some kind of a maximum as over partial sum. So was some max over partial sums. And so as a result, one important observation was to notice that we can discretize the starting points. There were just too many of them when n goes to infinity. And finally, when we want to control the maximum of the partial sums, we just control this by using Kolmogorov's inequality. Okay, so in the next section, when we prove some similar result of convergence to a Brownian bridge, since our processes will again be on the space of continuous functions, the starting point will be very similar. So we have to use this characterization using modulus of continuity, and so we have to see in a specific situation, what the modulus of continuity looks like and how we control it, what kind of inequalities or other ideas involved in order to control that probability and to show that this condition for the modulus of continuity holds and uniform tightness for our processes hold. So we'll see another example of this in the next section.